We're given an array of numbers and an array representing requests, and our goal is to find the best permutation of nums such that when we add all requests to that specific permutation, we're maximizing our sum. Let's walk through an example and see how we're actually getting this output for this sample input. So if we were to write out two permutations, we can see how we use the request to get an actual sum. So imagine our first permutation is the exact same as the input. So we have 1, 2, 3, 4, 5. And I'll label these with indexes. And now what we're saying is that to calculate the sum, we're going to add all the requests from index 1 to 3, and then we'll add the requests from index 0 to 1. And so that'll give us 5 plus 4, which is 9 plus 3, and so that is equal to 12. Now let's take a look at another permutation, and the second permutation is actually going to be our answer for this solution. So if I were to write out a second permutation, which would be 3, 5, 4, 2, 1. Similarly, if we follow the same steps, we'll see that we're adding up these three numbers, and then we're adding up these two numbers. And when we sum those together, we'll get our sample output, which is 19. And if we were to generate all the permutations for this possible array, we would see that 19 is in fact the maximum possible sum we could get from our given requests. If we take a look at what the question is asking us to do, we probably arrive at a brute force solution that looks something like this. So for every permutation of the input array that we're given, we're going to initialize a sum to 0, then we're going to loop through all the requests, and for each request, we're going to add those values in the array. And then after we process all the requests, we'll keep track, or we'll update the maximum sum. And you can imagine if we put this pseudocode inside a function, we would be returning the maximum sum at the end of that function. And that's the brute force solution. If we look at the pseudocode here for our algorithm, there's really two places that we can optimize. So the first being the outer loop, and then the second being the nested loop. We'll see in the final solution, or the most optimal solution, that we're actually able to optimize on both loops. But first, we'll need to start with the nested for loops and how we're calculating the requests in order to optimize for the permutation part. So if we take a look at the two drawings for the examples that we have here, we should notice a pattern. And that pattern is that the shape of the lines is the same regardless of the permutation that we're calculating the sum for. So what we're going to do is, instead of processing requests as a 2D array, right? So we're given a 2D array, we're actually going to convert that into a 1D array that's going to allow us to calculate frequencies or calculate the sum of requests a bit quicker. And we can kind of think of this transformation from a 2D data structure to a linear structure as a hit counter. So what it's going to do is going to convert this 2D data structure into a 1D data structure. So if we were to walk through step by step, initially what we're going to do is we're going to initialize some counter, right? And it's going to have zeros, and it's going to be the size of our input array, right? Because we want to keep track of the number of times an indexed element has been hit, so to speak. And so if we process the first request, we're going to add 1 to all indexes, 1 through 3, and this will be our new hit counter. And then if we add the second request, so if we're looking at 0, 1, and we add that to our hit counter, or we update our hit counter, what we're going to get is 1, 2, 1, 1, 0, right? And this is going to be our final hit counter. And so now what we can do is we can actually use kind of like a scalar product. So we can say when we're calculating the sum, instead of looping through, right, each request and iterating through our nums array, we can just multiply these numbers to one another, and then we can calculate our sum. So let's replace the code we've written in our brute force solution. When we compare this solution to the previous solution, so comparing it to the brute force solution, we'll see that we actually have a slightly better time complexity, and this comes from the fact that we're not iterating over these requests for every permutation that we calculate. We're kind of only doing this work once, so we're pre-processing the data, and then we're using the pre-processed data later on in a calculation. We are still bounded by the n factorial that comes by generating all the permutations, but we'll see at the end of this video how we can get rid of that factor. For the second optimization, we're going to be optimizing how we build our hit counter for requests. So if you take nothing away from this video, I want it to be this one technique I'm about to cover. So I'm going to introduce a more efficient way to build up our hit counter. Imagine we have the following input. So I'm just going to leave R as shorthand for requests. So imagine our requests, we're given something like this. Basically, we're given requests that have really large ranges. And so if we're going to iterate through these ranges and increment values one by one, we'll see that that's going to cost a lot, or that's going to be a very time-consuming operation. And so the question we're going to ask ourselves then is, can we use these two values to store some information? It turns out that we actually can, and let's take a look at what that looks like. What we're going to be interested in here is the starting and ending index for requests. So let's build a smaller example here. Let me erase some things. Right, so these are our requests, and we're only interested in the starting and ending point. So we're still going to initialize our hit counter the same. So hit counter is going to be, we'll say 0, 0, 0, 0, 0. Right, those are our 5 values. I'll add in the indexes here because that's what we're primarily interested in. 2, 3, 4. And now what I'm going to say is for each request, I'm going to increment the value of the starting location, and I'm going to decrement the value of the ending location plus 1. And what this is going to represent is this is going to represent a range. So if we repeat this process for each request, we'll see that after adding 1, 3, we have that. So after adding 0, 1, we'll see 1, 1, negative 1, 0, negative 1. And we're getting short on space here, so we'll go to the right. And after we process the fourth request, what we're doing is we're saying, okay, this is 2, 1, negative 1, 0, and negative 1. All right, so after we processed all our requests, we have this new structure here, HC, for our hit counter. We're still not there yet. We still need to, the goal is still to create the same hit counter we had before. We're just trying to minimize the number of times or eliminate the fact that we had to iterate through these indexes. So the fact that we had to iterate through 0, 1, 2, 3, 4. And so now what we're going to do with this hit counter is we're going to look at all the values in this range, and we're going to say set its value to be equal to the current value plus the previous value, right? So if we do that, we have 3, -1 plus 3 is 2, 0 plus 2 is 2, and 2 plus -1 is 1. And so after we've gone through this hit counter, we will have our resulting hit counter. Now that we've established the idea of a hit counter, we can improve our algorithm and get rid of the part where we calculate all the permutations. So if we think about what the question is asking us for, we can actually express it as a mathematical formula. So using a hit counter, we can say we're trying to maximize the following value. So we're maximizing the sum, where the sum is equal to some number times 1 plus another number times 2, and I'm getting these 1 and 2's from the indexes in our hit counter, plus another number, so C times 1 plus another number, D times 1, and plus another number, so we can say E times 0. We can really ignore this number, but for the sake of writing out the formula, we'll say that our goal is to maximize this. So how would we maximize this? Well, it's actually quite simple. What we want to do is we want to say, take the largest values, so take the largest values in the hit counter and pair them with the largest values in nums. And instantly, what your mind should go to when we're thinking about pairing the largest values in two lists is that we can sort the lists, and then we can just use 2 pointers to traverse and get our solution. So what that looks like is if we sort nums, well, nums is actually already sorted, but I'll write it out here so we can see what our final solution would be. So this is nums. I'll rewrite hit counter over here so they line up. So hit counter is going to be sorted. So we say 2, 1, 1, 1, 0. And now our sum, right, if we look at this formula, our sum is actually just going to be these values multiplied by one another. And then if we add those all together, so 5 times 2, 4 times 1, plus, and then 3 times 1, 2 times 1, 1 times 0, we add all that together, what we'll get is 19, which is our solution. So recapping the optimal solution, what we're going to do is we're going to first build this hit counter. Then second, we're going to sort nums and the hit counter. And then the third step is going to be, we're going to iterate through these two data structures, and we're going to sum up all the values, or multiply and sum up the pairs of values, and we'll return our result. And the reason this works is that the question is asking us to look at all permutations of nums. So another way of thinking of this problem is we can say, choose the permutation where 5 is located here, right? And then choose the permutation where 5 and 4 are located in those points, and 3 and 2, right? And we're kind of placing all our values greedily, but because we're allowed to use, or because we're searching for the maximum in all the permutations, we'll actually get the most optimal solution and the correct answer. And so real quickly, if we're going through the time complexity, and so the first step where we build this hit counter, we're going to say that that takes O of R time, right, where R is equal to the number of requests. And then for the second step, we could say that we are sorting nums and we're sorting hit counter, and those are both going to be of size n. So the second step would be n log n, right, n log n. And then for the third step, so the third step, sorry, this is kind of messy. The third step is we're looping through these two lists with 2 pointers, and that's just going to take O of n time. So if we look at all 3 of those, we can say that the time complexity is going to be n log n, and then the space complexity will just be O of n.